So we know that if a function is representable by a series, the series looks like this. That's called a Taylor series. It's called Taylor series centered at A. Who was Taylor? Who knows? What was his first name? I don't know. Bob. Bob Taylor. Maybe it was LaWanda Taylor. I don't know. Maybe it was a girl. It was Julie Taylor. I have no idea who it was. Anyway, if the series converges, this equality holds. And if this function can be represented by its series, which is not always the case, and that's a question for a later discussion. So if we do the Taylor series and we use our A to be 0, then that gets another name. It's called the Maclaurin series. Who is Maclaurin? Nobody knows. Well, all right, I don't know. I'm sure lots of people know, but I'm not one of them. Taylor and Maclaurin, they just got to put their names on these things. And why is it a different name just because you put A equals 0? I don't know. Maybe Taylor owed Maclaurin money and he had to put his name on it or something. I don't know. Anyway, so the Maclaurin series is the same as the Taylor series, except since the A is 0, you don't see an A there. And since the A is 0, you see a 0 right there. So Maclaurin series are sort of like the basis for the Taylor series. They're like the centered at 0. So it's like a default case, I guess we could say. All right, so how could I find the Taylor series for something like e to the x? And we'll start with the Maclaurin series. We're going to do, starting out with Maclaurin series here. We're going to do Maclaurin series for f of x equals e to the x. And we're also going to find the radius of convergence. So we're going to find these two things. All right, so finding the Maclaurin series, it starts with laying out all the derivatives, right? So we want to know what f of 0 is and what f prime of 0 is and what f double prime of 0 is. And there's lots of different ways you can organize this. I'm just showing you one way to organize it. And we'll see what each of these things are. So I know that f of x is e to the x, so f of 0 is e to the 0. And then for my derivatives, e to the x is nice. All the derivatives are e to the x, so all my f primes are e to the 0. So in this case, as I'm writing out this tabular form, it's sort of pretty redundant because I get the same thing every time. But you'll see, for example, if our function was sine, so it went sine, cosine, negative cosine, this table form is going to be really useful. And then what I do is lay out what are the c sub n's in each case. What is c sub 0, c sub 1, c2, c3, etc. So I just remember that what I've got here is the nth derivative at 0. What I need it is to be the n factorial in the denominator I need over here. So I just go 1 over 1, 0 factorial is the first one, 1 over 0 factorial, 1 over 1 factorial, I'm just transferring this 1 to the numerator, 1 over 2 factorial, 1 over 3 factorial. So those simplify to 1, 1, 1 half, and 1/6. But of course they go on forever, so we have to think about how that's going to look. We have to come up with a function for it. So what I can see is that my sum from n equals 0 to infinity of fn, the nth derivative at 0 over n factorial times x to the n, the Maclaurin series is, well, one thing that I need to make sure that I add on to here is the powers of x. So this is x to the 0, this is x to the 1, this is x to the 2, this is x to the 3. So my actual term of the sequence is, it's going to be 1x, x squared over 2, x cubed over 6, etc. Right? So what I have then is 1 plus x squared over 2 plus x cubed over 6 plus etc. And I want to write that as a nice formula, so I say that equals the sum from n equals 0 to infinity of x to the n over n factorial. All right, so that's what the Maclaurin series is. Now, if I want to find the radius of convergence, so I have this, when it converges, I have e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. All right, so if I want to find the radius of convergence, I do ratio test. So for ratio test, I need to look at a sub n plus 1 over a sub n. And that's going to be x to the n plus 1 over n plus 1 factorial times n factorial over x to the n, and that is going to simplify to x over n plus 1. And then I just look at the limit, as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And that equals the limit as n approaches infinity of absolute value of x over n plus 1. For a given x, x is bounded, n plus 1 is increasing without bound, so that limit is 0 for all x. So that means that the series converges for all x. The series converges for all x, which in this class really means for all real numbers x. Yeah, so that's nice. So that means that e to the x is actually equal to this sequence, this series that converges for all real numbers. Now, what we have not proven is that e to the x is actually equal to the series for all real numbers. We're going to hang on, save that for later. For right now, I'm just going to tell you it is. E to the x is equal to this series for any value of x at all. So I'll show you what that means. We can say, let's find e squared. Well, let's check e squared. Find e squared. So that would be e squared is equal to the sum from n equals 0 to infinity of 2 to the n over n factorial. All right, I'm just in this series right here. I'm replacing the x with 2. So this is a cool thing because this is a transcendental function. It's one of the things that's hard to compute. So where we started with this question is, how does your calculator know things, or a computer know things like what's e to the 4th power, what's the ln of 1.7? Like all of those things come from Taylor series, and this is sort of how they work, because e squared, you don't have sort of an algorithm to compute that, but this just involves multiplying, dividing, and adding. And you have digital algorithms for doing that, so it sort of converts the problem into a computable problem. All right, so I went ahead and computed some of those. So here's this series evaluated with 10 terms. That was 10 terms. And here is what you get adding up 10 terms of this series, just 10. And look at what e squared actually is. It's 7.389056099. What we got was 7.388994709. It's pretty darn close for just 10 terms of the series. So here I did 15 terms of the series. Here's 15 terms, right? And I get 7.389056095. Compare that to the actual value of e squared. I guess I don't have that there. I have it up here. Compare it to this value up here, 7.389056099. You can see that they correspond all the way up to the 1, 2, 3, 4, 5, 6, 7, 8, 9th decimal place. So it's a very rapidly converging series. It's a rapidly converging series. And what really does that is the n factorial in the denominator. So n factorial gets very large very fast. Fun thing to play around with is see what is the largest factorial your calculator can do. It's probably not much more like 20. Or it's 20 factorial is already an enormous number. So this n factorial is getting very large very fast. That means that the partial sums, the remainder, what's left after I add up 15 partial sums, is very, very, very small. So that's why this series converges rapidly to this number.